Question, sort 5-element array. All right, yeah, the question. Yeah, let's, use these 5 elements. All right, yeah. So this one, yeah, you will see it will be much harder than the previous one. Yeah. All right, let's do first try. Yeah. First try. First try, okay? Because we had we have 4-element solution already, right? Yeah. Can we apply that 4-element solution first? Yeah. So first try, apply the 4-element solution first. Okay? Yeah. But we need 5 comparisons, right? Yeah. There is a cost you need to pay. So this step, you need 5 comparisons. Okay? All right. So after 5 comparisons, we assume we have an ordered array after 5 comparisons. Yeah. Ordered. All right. Then, next step, insert x5. How many more comparisons do we need? Insert x5.
We're using the binary method, then it's going to x3.
Right.
First.
Yeah. Then x2. Yeah. Yeah. So by that binary search type, method, binary method, insertion, yeah, we can call that binary insertion. So we need 3 more comparisons. So total 3 plus 5, 8 comparisons. Then question, is it the best solution? We need to see if it is the best solution. Okay? Yeah. But I give you the lower bound formula. It can tell us how close to the best solution. Okay? All right. Let's look at the lower bound formula. Lower bound formula. Yeah. The full name of this lower bound is lower bound formula for the comparison-based sorts. Comparison-based sorts. Okay? Yeah. All right. Because there are non-comparison-based sorts. Hard to understand, but there exists. Yeah. Here, see a comparison-based sort formula. The formula is ceiling function of n factorial. Okay? Yeah. Lower bound. Now we calculate log base 5 factorial ceiling function. Okay? All right. Yeah. 5 factorial 120, right? 120. 120 greater than 64, less than 128. So between 2 to the 6th and 2 to the 7th. Ceiling function, 7. Oh, sorry, lower bound, this formula gives us 7, but we get 8. There is one difference. One difference. Okay? Yeah. So that means there is a possibility you can do better. You can use 7 comparisons to sort 5-element array. Here I just say possibility. Yeah. The reason is, although here we say lower bound, the question is, you may not be able to reach the lower bound, right? Lower bound, it just tells us you cannot break it. You cannot do better than that. But it does not tell you you can always get it, right? Yeah. Lower bound, it does not mean you can always get that lower bound. The best you can do is the lower bound. If you can find a solution that equals the lower bound number, then it's optimal. Yeah. But it does not mean you can always get a lower bound solution. Yeah. Right? Yeah. So here we want to see if we can get this 7 comparison solution. All right. Yeah. So here the reason we want to understand the reason that why we do worse than this lower bound number. Because when you spend first 5 comparison on the first 4 elements, you may not use those 5 comparison the best way. You may not use it in the best way. Okay? Because the thing is, so here let me explain this way. Yeah. When we spend 5 comparisons, do we want to get a maximum amount of information, right? Because after we spend 5 comparisons, we need to get useful information. We don't want to waste our 5 comparisons. Yeah. The question is, after you spend your first 5 comparisons, the information you get here is not the maximum information. Because if you spend still the same 5 comparisons, you can do more than this. Okay? That's the problem. All right. Now, let's spend our precious comparisons, in some, stingy way. Yeah. Not try to, in a very generous way. Yeah. All right. Yeah. Here, let me talk about, there is a method called the tournament method. I mentioned that before, right? Tournament method. Yeah. Here, let's apply the tournament method. Tournament method. All right. Apply tournament method on first 4. Yeah. Because we want to have power of 2, right? 4, that's a power of 2. Yeah. So when we apply tournament method, okay. Yeah. Comparison 1, comparison 2, comparison 3. Comparison 1, we can assume x1 is the winner. Comparison 2, we can assume x3 is the winner. Comparison 3, we can assume x1 is the winner. Okay? Yeah. So after 3 comparisons, we want to, do some cleanup work. Yeah. All right. X1, we use diagram to represent the relationship. X3, X4, X2. This diagram, yeah, showing the relationship. Yeah. Easy to see, right? Yeah, yeah, all the information. Okay, all right. Then we have singleton X5. Yeah. We do not have any information. All right. But here we only use 3 comparisons, right? That means we have 4 more. Yeah, because we can set this is our target. Okay? Yeah. We target on the 7 comparison solution. Okay? The best possible solution. All right. But we have 4 more. Okay? All right. Yeah. Here, what's our next step? Important, the critical step. Any idea for the next step?
If we have a lower bound for 4 more comparisons, we can just compare x sub 5 to every other element.
Yeah.
That would be 4 comparisons.
That's right. Lower bound. What?
Yeah, if our lower bound is 7, and we
Right,
only use
right.
3 comparisons,
Right.
and we still
4.
have 4,
4.
then we can just, x sub 5, we can just compare it to every other element.
But element, then you are too generous.
Right.
Yeah, because after even I tell you the result, how can you guarantee you get the whole array sorted? Yeah, don't waste your comparisons in that way. Okay?
And then
Yeah.
we set some rules since we know that x1 is the winner of x1, x2, so we can just compare one of those elements to x5,
Yeah. Yeah.
right?
Although you can, the question is, can you solve the problem? That's the question. Okay. Yeah. So here actually this question is a hard one question. This is a hard question. Okay. This is a hard question. That means if you do not have sufficient background, for this class, because we did a lot of preparation, so at this point we have the sufficient background. So that's why for us, if you follow the right way, it's not that hard. But for the ordinary person, it's hard. Ordinary person means, so if you have a friend, working in IT industry, doing computer programming, so they know algorithm things, right? So if you have a chance, you can give this question: sort 5-element array with 7 comparisons. Usually it's several hours work, 4 or 5 hours, several hours work. So because they don't have our background, they just use their experience, their logic. If you use their own logic without our background, if they can solve it in 4 or 5 hours, that's a smart guy, very smart. Now we have our insertion, understanding, and this our improved version, the binary insertion. Here we apply binary insertion. Okay, all right. So here, our powerful tool, binary insertion. But when we apply binary insertion, here the situation is different, because our 4-element, it's not an ordered array, right? It's not an ordered array. Our binary insertion, we should apply it on ordered array, right? Yeah. But can we modify it? Yeah. So the condition is not completely satisfied, but close, right? Very close. So here we apply the binary insertion. It's not ordered array. We just accept second best thing. Yeah. Second best thing, we only consider the longest ordered chain. How about that? We apply binary insertion on the longest ordered chain. Here we have ordered chain, 3-element ordered chain, and it's longest. Can we apply binary insertion on this 3-element ordered chain? Okay, all right. Comparison number 4. After that, 2 other possibilities. You have comparison number. Yeah. So 4, I should write it close to this line. Okay. Then 5 here, 5 here. Okay. Yeah. After 2 more comparisons, can we get X5 inserted into the longest ordered chain? Longest ordered chain, right? Get it inserted, right? Yeah. So there are two cases, okay? Yeah, two cases. One case is, your X5 is on top, X1, X3, X4, X2. Okay. Or another case is X, yeah, the remaining three elements, the order is not that important. I just do one of the cases. Yeah. Typically these two cases, right? Yeah, all right. And X2 here. There. The last thing, we just need to put X2 in place, right? X2 in place. This case, X2 place, we do two possible comparisons, right? Number 6, number 7. This one, binary insertion, right? Put X2 in place. One is compared with the middle one, X5, number 6. Number 7 could be this case or could be that case, number 7. How about it? But still 7 comparison, right? So get the X2 in place. Total 7 comparisons. Here you can see the most important tool we use here, binary insertion idea. The binary insertion idea. If people do not have this background, then it's very hard. Then it's very hard. Yeah. 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 So, yeah. If any of you, have IT friend, yeah. So they just use their logic. Yeah. So you can challenge, them. Yeah. All right. Yeah. So we here, and after we get a 7 comparison solution, it's the best solution, right? It's the optimal solution. Yeah. Because we have our lower bound formula. We know nobody can do better than that. We can claim, nobody can use 6 comparisons to solve this problem, to sort 5-element array for the worst case. Nobody can do that. All right? Yeah. All right, yeah, so we finished this topic. Yeah.
Just one last question.
Uh-huh.
Say this comes up on a test. Say this problem comes up on a test. If I am solving this and I give you my previous idea that x to x5 can just be compared to all other 4 elements, would that be a wrong solution? Do you want that type of solution?
You need to tell me. You need to discuss the results. Yeah. So you need to. Yeah. Many students only tell me, I just do this comparison, but you need to do discussion. You need to tell me. So after the comparison has different results, right? You need to tell me under this comparison result, what you should do next. You need to give me all that detailed information. So I need to see how close to the complete solution. Yeah. So I based on that, give you a partial credit. Okay? So, yeah. So in any test, assignment, yeah. So many students just tell me, that's what I want to do. Compare. This one, compare with that. No discussion on it. Yeah. But that's not enough. How do you show me? You only tell me, but what's the solution? You need to tell me which element is the solution, right? Or, how do you solve it? Yeah. So that's the, when I do grading, I need to, try to, I put in a picture, so the whole solution, complete thing. But how much you go through toward the whole solution, right? How much information do you give me? Unrelated information, not unrelated. Yeah. I based on that to give you partial credit. Okay? Yeah. All right, so we finished part A. Let's move to part B. We still have half an hour, so let's do the introduction part. Binary search, yeah, now, yeah. So you can see, yeah, we already used partial idea of the binary search. First, I quit part A. Then I go to part O. What's wrong? Yeah. Well, I cannot see my bar. Oh, yeah, now I can see it. Yeah. Hidden. Yeah. Now I need to jump to part B. Yeah, here. All right. Yeah. All right. Yeah. And a selection problem. Yeah. So I need to talk about the general selection problem after the binary search. Yeah. B.1. Binary search. Here we use the elimination idea to understand binary search. Yeah. Anything wrong, just let me know. Yeah. Yeah. If sometimes I see look something strange, then I figure something could be wrong. Yeah. Yeah. All right. Yeah. Yeah. This time we are given an ordered array, the condition. Yeah. Okay. Then, and a search key V. Yeah. We need to find index I such that V equals A of I. Yeah. Here you can see our data. We have a structured data. The structure, what's the main structure of our data? This ordered data, it's a structured data. When we have ordered data, we should take advantage of the structure. Yeah. So you should not, waste this important information. Yeah. All right. Yeah. So here the idea, still, we use our, previous idea. We used many times. Reduce problem size by the ordered data property. So the ordered data, the information we have from the ordered data can help us do some important work. So what kind of important work? Make prediction. Make prediction, okay? If the data is not ordered, then it's very hard to make prediction. But if the data is ordered, we can make good prediction, okay? Yeah. So that's the important thing we can do. Yeah. All right. So how to take advantage? Yeah. So, all right. We need to explore the order property. Yeah. All right. Here. Given ordered array, now we want to find which element equals the given key. Which element whose value equals the given key number. Yeah. All right. Then you have many different choices. Yeah. So compare with anyone in this array. Yeah. So in all those different choices, the first question, which one is the best choice? For the worst case. Yeah. Remember, when you do any operation, you always need to think about the worst case in your mind, not the best case. Okay? So here. In our problem solving, because we always target the worst case. Yeah. For a complete solution, we need to focus on the worst case for a complete solution. All right. Then, when you do all those, you have so many different choices. you can make. Yeah. Yeah. For all those choices, you need to look at the worst case. You need to look at the worst case for all those. Yeah. So here, because you have so many different choices here. Okay. Yeah. But after the comparison, you need to do analysis on your result. That's why. So as you said before, if you only tell me what to do, and you do not give me analysis on the possible results, right? That is not enough. Okay. So here, after we do any of the options, we need to analyze what's the possible results. Okay. All right. Yeah. So here, after one comparison, what do we want to see is, because here we want to use the elimination method. Yeah. When we use elimination method, we want to use the ordered data property to help us maximize the elimination. Okay? Yeah. So use this order property to maximize the elimination. Yeah. Okay? Yeah. So that's what, how do we take advantage of this structured data? All right. Yeah. The more elements we can eliminate, the better, right? Yeah. The more elements can be eliminated, then that means it's the best way. Yeah. All right. Yeah. All right. So here the question. For what kind of comparison you can maximize your elimination? This is the question. Yeah. So your comparison could be the first one, second one, third one, any element. For which of the elements, when you do comparison, you can maximize the elimination? That's the question. Okay? Yeah. Think about that. And your elimination should be related to the worst case, not the best case. Okay? The best case, yeah, here, let me show you one best case. Here. Yeah. All right. For example, when you compare V with this element, the best case, you eliminate one element. For the worst, sorry, not eliminate one. For the best case, you eliminate all these elements. Okay? Best case, because you can eliminate more. It's better, right? But the worst case, you only eliminate one element. Yeah. Here, we need to use your worst case to measure your performance, right? Use your worst case. We do not use your best case. We use your worst case to measure your, overall performance. Yeah. So you can see. All right? Yeah. So here, okay? Yeah. The best case, when V greater or equal to the last element, yeah, because you can eliminate all the elements before that. That's your best case. Yeah. Yeah. But if V happens to be less than LL, then you can only eliminate one case, right? You can only eliminate one case. Yeah. Yeah. So that's very bad. Yeah. That's very bad. That means if you compare with the last element, it's very bad. Okay. All right. So then, yeah. So so here there is some, for understanding. Yeah. Because when we we need to make a decision. What is the best decision? When we make our decision, yes, here, yeah. So this Murphy's law can help us understand the situation a little bit. The Murphy's law tells us anything that can go wrong will go wrong. So that's the yeah. So here we do not argue it's correct or not. Okay, because here Murphy's law, many things can be explained by Murphy's law. Yeah, here, yeah, can be wrong, will go wrong. So all you can say could be wrong, could go wrong. Okay, whatever could go wrong. Okay, all right. That means, is it targeting the worst case idea? Yeah. So anything that can go wrong, we treat as the worst case. It's the worst case. Yeah. Yeah. Will go wrong, that means you should target this worst case. You cannot ignore this. So will go wrong, let's understand this way. Don't ignore this worst case. Yeah. Because some people feel we have chance to, without encountering the worst case. Yeah, we have a chance, right? So then people, when they make a decision, so they do not plan for the worst case. Because we have a chance to escape the worst case. Yeah. So then they do not make any plan. Yeah. So here Murphy's law tells us, you have to make your plan for the worst case. Yeah. Because just you assume it will go wrong, right? You cannot escape. Okay? You cannot escape it. You have to, target on the worst case. Murphy's law. All right? Yeah. Don't argue it's correct law. So that's some, strategy, mentality, right? Problem solving mentality. Yeah. All right. Yeah. So then, now you can see the best solution is compare one right in the middle. Compare the element, the position-wise, right in the middle. Yeah. Why this is the best option, best choice?
It eliminates half the data.
Yes. You can guarantee half of the data is eliminated. You can guarantee always, it's greater than that element or less than element. You can always guarantee about 1/2 of the data can be eliminated from one comparison. That's the essence of this choice. The essence. Yeah. All right. Because after that one comparison, you have two possible outcomes, and these two possible outcomes are equally well, right? Equally, from the results point of view, equal, almost equal. Yeah. Yeah. You drop the first half or second half, you get the same final result. Okay? Yeah. All right. Here, I may also like to refer to, question, Shaza? Yes, even odd, good. Yeah, that's a good question. So here, let me address that small difference. Yeah. So Shaza raised that question. Yeah, even odd. Odd you have no problem, right? You have one right in the middle. So now we need to, because for the even case, we want to, right? There are two elements in the middle, so they have the similar situation, right? Yeah. So here, we give a name for it. Yeah. Because the distance, the first one distance to the left end, and the second one to the right end, that distance is the same. Okay. Yeah. Two elements in the middle, and the first one we call the left median. Also median for the left median. We have two medians. Okay. Yeah, left median. Yeah, left. Then this one, right median. All right. And when we do binary search, we don't want to, make a guess. These two. Yeah, actually, these two equally well. Yeah, but we want to make it certain. Yeah, yeah, make it certain. So we always pick a left median. Okay. When we have two medians, left or right, so by default, we select left median as our default median. Yeah. So right median, you need to specify it. Okay. If you don't say anything, then you do not use right median. Okay. Yeah. So the default median is the left median. Yeah. All right. Yeah. So then you have no confusion. Yeah, no confusion. Okay, all right. All right. Then here regarding, because you explain when we select the one in the middle, including the left median case, okay, we can eliminate approximately 1/2 of the elements. 1/2. All right. And this idea, I also want to use another different understanding. So that understanding also very interesting in our problem solving. So what's that? That argument is called an adversary argument. Adversary argument. Yeah, let me explain this adversary argument. Yeah. This idea actually quite useful in our problem solving for this class. Yeah. In our second half. Yeah. First half, we didn't use this. The second half, yeah. So sometimes you can use this to help you. Yeah. Because our goal, we target the worst case, right? We always target the worst case. Yeah. The question is, how do we get the worst case? It may not be that easy, right? Yeah. So we have so many cases. How do you find the worst case quickly, right? Yeah. Because when you solve a problem, you need to make many decisions, right? Yeah. A sequence of decisions down the road. Yeah. And to choose the right path, it's not easy. Yeah. So at every turn, you choose the right direction. That's not easy. Yeah. All right. So here, we use a smart adversary to help us make that decision. Okay? Find the right path. Yeah. All right. Here, we describe this smart adversary. Yeah, because this adversary is very smart. Okay. Every time when we make a decision, we ask our adversary, yeah, which option you want to give us. Yeah. Because that adversary always want to give us an option to make our life harder, right? Yeah, the adversary won't make our life easier, right? Yeah, that's the natural behavior of the adversary. Always make our life harder. Then that's the worst case, right? Yeah. So every time when we need to determine, so we have several cases. So which one we should take? Yeah. So you can assume. So you throw it to the adversary. So the adversary will pick the worst one. All right, here, let me use the adversary argument to explain. So when we make comparison, okay, V compared with any element in this array, then when you select some element somewhere, that element split the original into two arrays, two subarrays, right? Usually, one is longer, one is shorter, right? Yeah. All right. Then, which subarray should be eliminated? Then we ask our adversary, which one you want to make us to go? Which way to go? Yeah. The adversary will say your element should go to the longer subarray, not shorter. Shorter elimination, the adversary will tell you your result, your comparison result, can only eliminate the shorter subarray. Then, the comparison result, you need to go to the longer subarray to do the further search. Okay? Then the adversary would force you to do more work. Do more work. Okay? We need to go to the longer subarray to do more comparisons. So it forces us to do more work. That's the adversary argument. Okay? Yeah. Yeah. Just the thinking here. Okay? Yeah. Because sometimes you need to do understanding. So this is used in your understanding. Okay? Yeah. All right. So here, now, we want to find the right strategy to beat our adversary, right? Yeah. So our strategy is we compare V with the element in the middle, then that middle element split the array evenly. The two subarrays they have the same length. Then when you ask your adversary The algorithm can pick any one of the two, no difference. So that tells you when you have chance to make decision, you want to make a balanced decision. Yeah. The decision should be balanced. Okay? When you make a split, the split should result in the two subarrays with even sizes, yeah, almost even sizes. Balance the split, because this is the best strategy against your adversary, right? The adversary pick anyone, no difference. Okay. So that's our strategy to beat adversary. Yeah. All right? Yeah. So after that, now, yeah. So here, yeah. So here we can call some balancing principle. Okay? Yeah. When you have chance to split your data, make a balanced split. Make a balanced split. Then you can get the best results for the worst case. You can control the worst case. The worst case won't be very bad. Yeah. So that's the idea. Yeah. That's strategy. All right? Yeah. All right. So here, we point to efficiency analysis, binary search. Okay. Right. After we understand that, yeah, next, yeah, so for the binary search, yeah, here we need to do some analysis. Yeah. All right. The analysis, we want to calculate the number of comparisons for the worst case. Yeah. Number of comparisons for the worst case. Yeah. So at this point, actually, all of you, I think, you have some idea about the worst case of the binary search. Given n element array, yeah. If I ask you, what's the number of comparisons for the worst case? Yeah. Many of you have at least have some idea, right? Yeah. Many of you have some idea. Log of is 2, right? Log of is 2, right? Log is 2 of it, but this number may not be an integer, right? May not be an integer. Yeah. So then you need to make it integer number for the worst case. Yeah. Then you may take a floor function or ceiling function. The question, should you use floor function or ceiling function? Okay, yeah. The two options. Yeah. Two options. Floor function ceiling. So many students doing that way. Okay. So here, the final answer. Okay. So here, if you need to, so here we want to get exact number. Not approximate number. So here we want to find the worst case of the binary search, exact number, exact expression, okay? Not the approximate expression. Exact expression, neither one is correct, okay? So yeah, there is small difference. Neither one is correct, okay? So for this one, actually, this one, plus 1 is correct. 1 plus floor function is correct. Okay, yeah. Plus 1. Yeah. For this version, you need to make a modification. N plus 1 ceiling function. Plus 1 inside the parenthesis, not outside parenthesis. Yeah. These two formulas both correct. Okay, they are the same. It's not easy to see, but they are the same. Okay. Yeah, we will see it. Yeah. So I will derive these two formulas. Okay, all right. Now, here, we need to do some analysis work to see these formulas. All right. Let me show you. This line segment represents the whole array. All right. Here we do estimate. Yeah. So not exact. Yeah, we do estimate. Yeah. All right. Then we know when we compare the element in the middle, we can drop one half of the data. So using the sizes, yeah, 1/2 of the data size could be dropped. One comparison, 1/2 dropping. Yeah. Second comparison, second half dropping. Yeah, yeah. All right. So we do it all the way down to the end. The question is when to stop. How do you know you can stop safely? Yeah. You cannot do it forever, right? You have to stop somewhere. Yeah. All right. So here we want to use the data sizes to tell us when to stop. Yeah. So here, let's look at it. After one comparison, the data size is 1/2 of the original size. Two comparison, n over 4, 2 squared. 4 is 2 squared. Okay, yeah, the sizes. After k comparison, the data sizes remain so this much. N over 2 to the kth. That's the data size. Yeah. All right. And this number, when you see this number, we want to use this number to tell us we already reached the end. We already reached the end. Yeah, we'll use this number to tell us. All right. Yeah. All right. So what property do we use here? Well, we want to determine the last comparison. Last comparison. All right. Yeah. The data size, here we use a small line segment to represent the data. Yeah, because this number, we use this number to represent the length of that line segment, right? The length of that line segment is this much. There is a number for it. Okay? All right. Think about when that number is very, very small, it can only cover one number. That little line segment can only cover one number because it is not long enough to cover two numbers. Not long enough to cover two numbers. Yeah? So that means you only have one data that falls into that small interval. Then no more split needed, right? You don't need any split. You only have one number while you split, right? Yeah, one number, one comparison, then you're done. Yeah. So no split anymore. Yeah. So that means if the length of that line segment is less than 1, then no split, right? Yeah. So that's our criteria. Yeah. Criteria. Yeah. Yeah. All right. Yeah. So if the data size strictly less than 1, if it's 1, there is a chance to cover two elements, right? Strictly equals 1, then still you may need to do one more split. Yeah. So, but strictly less than 1, then only one element can be covered. Yeah. All right. All right. Then the size strictly less, then the previous size. Yeah. Before this split, there is a previous size, right? The previous size should be greater or equal to 1, right? Yeah. The previous size, then you have another split. Yeah. So we need these two inequalities. Otherwise, your k could be too large, right? Yeah. If you do not use the, upper half, your k could be too large. Yeah. So here, the upper half, so you cannot make that k too large. You can only choose appropriate k. Not too large, not too small. Okay? So you need to use two sides for your criteria. Yeah. Yeah. All right. So related to this one. Yeah. All right. Then after simplification, we want to remove the common denominator. Okay? Yeah. Let's multiply that common denominator both sides. Yeah. So then we have this inequality. This inequality, you see power of 2. Yeah. In order to, get inequality, we take a log base 2. Log base 2. Yeah, so we don't have the power of 2. Okay? So we get this inequality. All right. Yeah. All right. Then, here you can see this side equal sign. K minus 1 less than or equal to log base 2 of n. Then this strictly less than, no equal sign. Yeah, that's different. That small little thing that could cause something different. Yeah. So you need to be careful. Yeah. You need to be careful when you see things like this. Yeah. All right. Then, so here, so we have this formula. Yeah. Yeah. Now, because here we want to estimate that k. K tells us the number of splits, right? So that corresponds to the worst case. Each split corresponds to one comparison. So this k number corresponds to the number of comparisons for the worst case. Yeah. All right. So we want to derive the worst case formula. Yeah. All right. Then, so this inequality we can change the form in this way. Change the form. All right. Yeah. Original. Yeah. So we want to keep the original because sometimes if we feel from derived inequality we may miss some information, then we need to go back to the original. Yeah, because when we change the forms of the formula, we may lose something. Yeah. But your original formula, you do not lose anything. Yeah. So that version, you do not lose anything. Yeah. So that's why I need to, stop quickly. Yeah. All right. Yeah. So here, we need to make some better improvement. We need to improve our formula. So here, it's about improvement. Yeah. Yeah, because this part a little hard to understand. Yeah. Let me leave to the next time. Yeah. Next time I explain. Yeah. How do we improve this formula? Yeah. So then we get the worst case formula for the binary search. Yeah. So that formula, most people, they use the closed formula, but not exact formula. That's very common. Okay. All right. So let's stop right here.